Hello, in this segment, I'm going to make some analysis of the affine cipher. We talked about the affine cipher construction in the previous segment. Very quickly, I will summarize it for you. The algorithm goes as follows, right? The encryption process is basically, suppose you have a letter that you would like to encrypt. Letter is alphabet letter, A through Z, for example. We map A to 0, B to 1, Z to 25, right? And we take the input X as a number. How do we do the affine transformation? We take the private key. There are two private keys actually. A and B are private keys, or if you want to call that one key. A and B together is one key. Okay, we send this mod 26 if you are working with English alphabets, right? English alphabet letters, there are only 26. Otherwise, you can select whatever number you like according to the alphabet set that you're working with. Let me call this as Y, okay? So X is your plain text. You multiply X by A and add with B and mod 26. X is one particular number, okay? To be more precise, X belongs to the set 0 through 25, okay? 0 means one particular encoding. 0 means A, 1 means B, and so on. And you send Y to the receiver. So the receiver will do the decryption as follows. He will take your Y, well, the Y that you send, and he will apply this opposite, of course. He has to first get rid of B. That means he needs to subtract B, right? So at this point, he has A times X. So he needs to multiply it by A inverse. Then he will get the X back. Okay, so this is basically how the again he has to do it in mod 26. This is the decryption process. Now the question is, A inverse, will it exist always? The answer is no. A inverse may not exist always. So I mentioned in the previous segment that the precondition for that is GCD of A comma 26 has to be 1. If this is true, then A inverse exists. But I didn't give you proof, or I didn't give you some details why we need this property. We know that A inverse will not exist if this is violated. So this is the key. Okay, B can be any number from 0 through 25, inclusive of both 0 and 25. A has to be relatively prime to 26, meaning if you take M is equal to 26, the modulus M to be 26. A cannot be 2 because GCD of 2 and 26 will be, what is GCD of 2 and 26 is 2. So that's not good. So A has to be relatively prime to 26. All right, let me show to you. I wrote a little Python program to generate the affine cipher, and then we can do some analysis quickly. What I'm going to do is show you my little Python affine mapping, right? X is a number from 0 through M, excluding M. So if you are working with English alphabet letters, M is 26, okay? That's by default. Now I'm going to print this affine transformation for different A's and B's and show to you how this thing actually works. So let me do much simple one first. Let me set my A to be, say, 3, B to be 4. And I set my M, the alphabet set, to be much smaller. Let's say my M is 5. Okay. So what's going to happen here is that 0 will be mapped to 4. You can plug in the value of A, B, and compute yourself. That's not difficult. 1 will map to 2, 2 map to 0, 3 map to 1, 3, 4 map to 1. If you pay close attention to the mapping, we see it is a one-to-one function, right? We see it's a one-to-one function because this set, right, and this set is just permutation of each other, right? Therefore, it's a one-to-one function. There's no double arrow, right? There's no point where 0 is going to 4 or some other element also goes to 4. That's not happening here. But now I'll surprise you a little bit with, say, GCD of A comma M not equal to 1. Okay, that means what will happen in that case? Okay, so let's try that. So I'm going to do is we'll call the affine program, but I will choose my M to be 6 now. Okay, so 3 and 6 are not relatively prime to each other. So we will see what type of mapping this will generate. As you can see, this is not generating a one-to-one permutation. For example, all the values that we are seeing on the range is just 4 and 1, right? So it's not a permutation of the input. 0 gets mapped to 4, 2 also gets mapped to 4. That means this is not a good encryption scheme, because given 4, you can't go back. You don't know whether the input is either 0 or 2 or 4. The three solutions, as we can see here. Okay, so that is one of the reasons why our A has to be relatively prime to M. Okay, let me continue now. Suppose I put my M to be 7. Again, we can see it's a permutation. 0, 1, 2, 3, 4, 5, 6 gets mapped into something that is just a rotation. Okay, that's good. But let's try 8. Okay, this is also good, because as you can see here, there is no, this is just a rotation of the input. Okay, all the numbers are present here, 0 through 7. Okay, let's try M to be 9. Now we get into an interesting situation. The range is just made of numbers 1, 4, and 7. That means not all numbers are mapped. Okay, meaning you can't invert 4 consistently. 4 could map to 0, 4 could also map to 3, 4 could also map to 6. So that's not good. Okay, so that's the reason why in the affine mapping, we want this is A, right? This is B, and this is M. We want A and M to be relatively prime to each other. Otherwise, we will get into cycles like this. Okay, or to be more precise, not invertible function. But if you enforce the property that A and M are relatively prime, let's make a longer one. Actually, for example, I made 3, 4, and 13. 3 is relatively prime to 13. You get a large length. Okay, meaning there's no collusion whatsoever. 2 different inputs don't collide to the same output. Okay, this is basically a one-to-one function. Okay, and if you extend this further to a 26 alphabet set, right? I'm not going to go through again, but you will see that there's no collusion. Okay, maybe a little bit time you need, but you can confirm. Okay, so let's make it simple. Let's start with this again. If A and M are relatively prime, this is a one-to-one function, therefore it's inverted here. GCM is my modulus, right? In this case 26 for English alphabet. We need this. Okay, I'm going to now explain more mathematically why I need this. Okay, so let me do the analysis now. Suppose my function is defined like this, right? Ax plus b is what we are transforming our x to be. So we can rewrite it like as follows. As a sender, I take A and B as secrets, and the receiver also should have the same A and B. Somehow they agree on A and B before the communication. So the sender sends this value, right? He or she computes Ax plus B and performs mod 26 and sends the Y to the receiver. Okay, we need to argue why is this a one-to-one function. Okay, the reason why it is a one-to-one function is as follows. Let us assume for a moment the GCD of A and 26. I'm going to replace 26 by M because there's nothing specific to 26 per se. So I'm going to erase this a little bit and make this as M. Okay, so I'm going to call this as the modulus M. M can be 26, but it can be other than that as well. So let's assume the GCD of A comma M is 1 for a moment. Okay, what can we say now about the function? Is the above function a one-to-one? We can confirm that. One-to-one means given one input, we get one output. No 2 inputs map to the same output. Okay, and any output can be reversed uniquely to find the pre-image. Okay, all right, that's basically one-to-one function. So let's continue this discussion now. Suppose GCD of A comma M is 1. Can I now show to you that this function is one-to-one? Okay, how do I do that? Let us assume there is some collusion for a moment. Let's say A times x1 plus B happen to be equal to A times congruent to A times x2 plus B in mod M. Okay, so I'm not going to write the mod M. You can write it if you want. So you can now subtract both sides by B. Therefore, we get A times and rearrange this a little bit. So you get a times x1 minus x2 is equal to, is congruent to 0 mod m. Okay. So what does this tell us? This tells us that now I have to write mod m here. This tells us that m divides a times x1 minus x2. Otherwise, you will not get this equation, right? So m divides a times x1 minus x2. Okay, but we do know that a and m don't have any factors, right? There is no common factor between a and m other than 1. That means from the properties of number theory, one of the properties I must say, that if m doesn't divide a, that's because of GCD of a comma m is 1. That means m must divide x1 minus x2. Otherwise, m wouldn't have been able to divide the product of these two numbers. Okay, this is a key. This implies m must divide x1 minus x2. Okay, and now we can complete the proof quickly. This means that x1 must be equal to x2, congruent in mod m, right? That's the definition of congruence. We talked about modular arithmetic congruence earlier. When m divides x1 minus x2, we can rewrite it as x1 is nothing but x2 in mod m. Okay, which is exactly the meaning of one-to-one. You assume there's a collusion and then you show that the inputs are the same. Okay, so we went in one direction. We assumed GCD of a comma m is 1. We proved that this is a one-to-one function. Now we can go backwards, meaning given that the function is one-to-one, we want to argue that GCD of a comma m is 1. How do I do that part? So let me explain that now very quickly. Suppose we know the function is one-to-one and we want to argue that GCD of a comma m is 1. So I'm going to use proof by contradiction kind of technique to prove that. So I'm going to argue what happens if my GCD of a comma m is some number d, right, which is more than 1. Let's say is some number d, right, more than 1. Okay, in that case we need to think about how we can produce some contradiction. The contradiction we need to show is that the initial assumption. What is the initial assumption? This function is one-to-one. Let me try to show that this is not one-to-one. Okay, because we made an assumption here that GCD of a and m is more than 1. Let's try to make this assumption 1 and then try to prove that 2 is not one-to-one. Okay, which is wrong because we started with one-to-one assumption. Okay, we need to do that now. So let's assume GCD of a comma m is d. Okay, more than 1. So I'm going to do this small trick now. We write the equation number 2 as follows. We write ax is congruent to y minus b mod m. Just rearrange the b a little bit, mod m. Okay. So if you fix a b, which is the case, right? We fix a b, and if we vary y, y minus b will vary as well. Okay, y minus b will generate all possible m values. Okay, all right. So let's rewrite this. So let's assume for a moment the scenario that ax turned out to be 0. It can happen, right? Ax can be 0 because y minus b will generate all possible values. So it must be also generating 0 at some point. Okay. And now let's think about the scenario of this equation number 3. So one solution is clear. X is equal to 0 is one solution. Okay. Because if you put 0 there in equation number 3, 0 times anything is 0. That's good. But I'm going to show to you there is at least one more solution. Okay. What if my x is say m by d? M by d must be an integer. Remember, because the GCD of a comma m is d. That means m by d must be an integer. So what if my x is m by d? Well, we can put it now here, back to equation number 3. A is a multiple of d. That's the reason why GCD of a comma m is d. So d and d will cancel out. So what you will have on the left hand side is some multiple of m, right? Which means you found out two solutions. This is one solution. This is another solution. So let me clarify the second solution. If you put x is equal to m by d in equation number 3, so you have a times m by d, right? But A itself is a multiple of D because we know GCD of A comma M is D. That means I can rewrite it as follows. I can replace this A by some say okay, some ZD, okay, because A comma M is D, that's the meaning of GCD. So that means this D and this D will cancel out. So what you're left with is a multiple of M, right? When you do mod M, you'll get 0. That means you found two solutions, okay, which is not good, because what you're arguing now is that you have input 0 mapping to output 0, and you have input M by D also mapping to 0, which means this function that you are dealing with is not a one-to-one function, okay? That's a contradiction, because we assumed the function is one-to-one, and we wanted to prove that the GCD is 1. What we did is, by proof by contradiction, we assumed GCD is more than 1, so therefore we tried to prove our initial assumption is wrong, and so we found out that the initial function must be not a one-to-one function, okay? So to summarize, the long story short, the solution for the equation number 2 is only possible for given y, to find the x is only possible if A and M are relatively prime to each other. Okay, that's basically the analysis of affine cipher. Okay, in this next segment, I will show to you how you could do frequency analysis or known plain text attack to recover A and B if you are given a pair of plain text and ciphertext. Okay, that's the next part of the presentation will be. Thank you very much.